Greetings, folks. Welcome. When economists use regression analysis, it's often with the purpose of conducting a hypothesis test about a claim we might have about a population. When we conduct a hypothesis test, we often start from a regression model. This is our idea of how we think the world works, and I've always thought that there's a relationship between the grade a student gets on a test and how much studying they do. So here's a peek at my population regression model. Grade equals beta subscript 0 plus beta subscript 1 times hours of studying plus epsilon, where epsilon is the error term, which would capture anything else that might affect your grade on a test. Unfortunately, I don't have access to the population of all students, so instead I'll do my regression analysis using information from a sample. So the sample regression model is grade equals b subscript 0 hat plus b subscript 1 hat times the amount of time spent studying. So let's go through the 5 steps of doing a hypothesis test. The first step is writing out the hypotheses. So my claim is, I think that studying has an impact on a student's test score. So we often write the claim as the alternative hypothesis. So this is H subscript A is that beta 1 is not equal to 0. Whereas a null hypothesis, written as H subscript 0, is that beta 1 is equal to 0. So if the null hypothesis is true, that means that the effect of studying on your grade is 0, or that there's no effect. But of course, my claim is that there is an impact. In other words, beta subscript 1 is not equal to 0. The second step is deciding on the significance level. This is a probability of making a type 1 error, of rejecting the null hypothesis when it's true. The most common significance levels we use are 10%, 5%, 1%. In this case, I'm going to use a 5% significance level. The third step of a hypothesis test is a fun part. That's when we conduct the research. So here we have information on a sample of 40 students. You see a scatter plot showing the relationship between their test grade on the y-axis and hours studied on the x-axis. My regression result is beta 1 hat is 2.732. That says as you increase studying by an hour, it lifts your grade by 2.7 percentage points. And the standard error is 0.337. And I should say that both of these values, the beta subscript 1 hat and the standard error, come from regression software, computer software you use to estimate the regression model. The third step of the hypothesis test is to calculate the test statistic. And of course, it's a t-statistic where t equals b1 hat, this is the value from the research, minus beta 1 naught, this is the value for beta 1 from the null hypothesis. You divide that by the standard error of the sampling distribution. So of course, the b subscript 1 hat from my research was 2.73. You subtract from that the value from the null hypothesis, which is 0, and the standard error was 0.337. So I have a test statistic, or t-stat, of 8.11. The next step of a hypothesis test is to find the p-value that corresponds with the t-statistic you just calculated. A p-value provides an idea of the strength of the evidence in favor of the null hypothesis. It's a probability that, if the null hypothesis is in fact true, you could get a value that is more extreme than the test statistic that you calculated from your sample. To find the p-value, we'll go to a t-distribution with 38 degrees of freedom. We had a sample of 40 observations, and if you have a regression model with one explanatory variable, you have n minus 2 degrees of freedom, so that's 40 minus 2, so 38 degrees of freedom. And we need to find the area to the right of a t-statistic of 8.11. So if you look at this t-distribution, you'll see right off that there's very, 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 very little area under the distribution that's to the right of 8.11. In fact, looking at it here, it's almost like it would be 0. But to be sure, let's look at the t-distribution table. Of course, the t-distribution table shows the upper tail for a certain number of degrees of freedom. We'll go down to 38 degrees of freedom, and we're looking for a t-value of 8.11. So if you start going across that row, you see a t-value of 0.851, then 1.304, then 1.686, then 2.024, then 2.429, and then the last value is 2.712. So there's no value of 8.11. So all we know right now is that the area under the t-distribution to the right of 8.11 is less than 0.005. Because our table just isn't precise enough to give us the exact value. Now we can go back to the t-distribution and put in that the area under the distribution to the right of 8.11 is less than 0.005. So now for the p-value, of course bear in mind that this is a two-sided hypothesis test, so we actually have to multiply that value of less than 0.005 by 2, which gives us an approximate p-value of less than 0.01, or say less than 1%. This means that there's less than a 1% chance that if the null hypothesis is true, that is, in fact, if the time spent studying has no effect on your score, you could get a value that is more extreme than the test statistic of 8.11 that we got from our sample. With this p-value of less than 1%, or 0.01, there is very weak evidence in favor of the null hypothesis, which means that my claim is probably true. The last step of the hypothesis test is to compare the p-value to alpha. So in step 2, we set a significance level of 0.05. That was our alpha. That meant that we were willing to tolerate a 5% chance of rejecting the null hypothesis when it was true. And with a p-value of less than 0.01, there's less than a 1% chance that if the null was true, we would get a test statistic of 8.11 or higher. And since the p-value is less than alpha, we can reject the null hypothesis in favor of the claim. In other words, we can say that with a 5% significance level and based on a sample of 40 people, the amount of time spent studying impacts your test grade. So what are you waiting for? You need to start studying for your next test.